When the University of Alberta announced it would award David Suzuki an honorary Doctor of Science degree at its spring convocation, there was, and continues to be, a vocal backlash. Critics argue his stance against Alberta's oil sands make him an unsuitable recipient. Although Suzuki is receiving the honor because of his efforts to boost science literacy and environmental awareness, it's important to remember that before he became a broadcaster and an activist, he was a globally recognized scientist. Born in Vancouver in 1936, David Suzuki and his family, all Canadian-born citizens, were subjected to the unethical Japanese internment during the Second World War. The Canadian government sold the family's dry cleaning business, interned them and sent Suzuki's father to a labor camp. Despite these setbacks, Suzuki embarked on a career in science with his first professorial appointment in the genetics department at the University of Alberta in 1962. David Suzuki, Centre, poses with protesters at an entrance to Kinder Morgan in Burnaby, BC, on Monday, March 19, 2018. Numerous protesters protesting the Kinder Morgan Trans Mountain Pipeline expansion were arrested. The Canadian Press, Daryl Dyke, today, as a dedicated scientist and communicator of science, Suzuki frequently presents the scientific case for climate change and the effect of fossil fuels to the public. No other scientist in Canada has been pilloried so strongly for simply presenting the data. Nobel nod. While many may think of Suzuki as an activist or a television presenter, he also holds a legacy in genetics research that contributes to the foundation of knowledge and advances in the life sciences. Jeffrey Hall, Professor Emeritus of Biology at Brandeis University in Waltham, Mass., was part of a trio of scientists awarded the Nobel Prize in Physiology or Medicine in 2017 for their work on discovering the molecular mechanism behind circadian rhythms, the body's internal clock. In an interview prior to this recognition, Hall was asked, "Do you have any other heroes, as it were, among researchers in your field?" Hall identified Suzuki as one. The genetic world reacted to Suzuki's approach and accomplishments as if they were genuinely sensational. So what was this breakthrough made decades ago by Suzuki at the front lines of genetics research? As a professor at the University of British Columbia, Suzuki wanted to understand how muscle worked and tried to uncover genes that would cause paralyses. He reasoned that such genes would be in common to all life forms with muscle. He selected the common fruit fly, Drosophila melanogaster, for his experiments. This was genius. Suzuki's discovery. It's worth highlighting the beauty of Suzuki's strategy because this legacy and approach has stood the test of time. Until that time, research on fruit flies was considered esoteric and narrow. In Hall's view, Suzuki's work was crucial to the resurrection of Drosophila from the ash heap of biological research. Suzuki's experimental design was elegant and conclusive. He simply fed fruit flies a chemical known to cause random mutations. In 1967, Suzuki was the first to use temperature to screen for genetic mutations in fruit flies. These temperature-sensitive mutants behaved normally when the flies were kept near room temperature, 22. The effects of the mutation were only observed at a higher temperature, 29, he later wrote in Science magazine. The fruit fly Drosophila melanogaster is a model organism used to understand the biology of other organisms, including humans. Shuttershock. At the high temperature, some of the flies became paralyzed and fell to the bottom of their container, while unaffected ones simply flew. When he changed the temperature to 22, a small number of the paralyzed fruit flies at the bottom of the container regained the ability to fly. The flies' recovery after the temperature change meant they harbored a mutation in a single gene. Suzuki named the gene Shibir, the Japanese word for paralyzed. A dynamic outcome. Other scientists determined the Shabir gene codes for a protein named dynamin that controls small structures found at the junction between nerve and muscle that house the chemicals necessary for muscle contraction. A mutation in Shabir prevents muscle contraction and results in paralysis. In humans, such mutations are linked to neurodegenerative diseases, including Charcot-Marie tooth disease. Today, about 5,000 scientific publications on dynamin reveal a function common to all life forms with nuclei in their cells, that is all animals, plants, yeast, flies, etc. Suzuki went on to show several examples of mutations in single genes. The second gene Suzuki discovered was named stoned, since the flies had uncoordinated wing and leg movement. Today, we understand that this gene encodes for a protein that also affects the same fundamental machinery as dynamin. It was not long before the international community of discovery researchers followed Suzuki's lead. He had correctly predicted that studying genetic mutations in fruit flies could help scientists identify genes involved in the development of human disease and other phenomena. History will judge the outcome of Suzuki's attempt to use observation and reason to advance scientific literacy, appreciation of nature and knowledge of the ecological crises threatening life on the planet. But it remains that Suzuki may be considered Canada's pioneer in fundamental genetics research. John Bergeron gratefully acknowledges Kathleen Dixon as co-author.